In this work, we present collaborative filtering using preferences inferred from brain signals. Here we demonstrate, for the first time, the use of subjective preferences predicted from brain signals in a content recommendation system. Whether it's entertainment providers creating personalized music and movie recommendations, news aggregators recommending articles that cater to a reader's particular interests, or online retailers suggesting products for customers, content recommendation has become ubiquitous across the web as a way to contend with information overload. Collaborative filtering, one of the most popular approaches to content recommendation, is a technique in which data from many users are used to inform personalization systems and tailor content to better match an individual's needs and interests. Since its early applications in filtering email mailing lists, collaborative filtering has become a widely researched topic in academia and a technique used across various industries. A primary focus has been to develop new mathematical techniques that offer better results and more effectively utilize the ever-increasing amounts of user and content data. However, the performance of collaborative filtering is not solely dependent on the computational method used. It also depends on the quality of the signal used to estimate user preferences. Improving existing collaborative filtering methods is not simply a matter of acquiring more data or using a more complex model. Instead, significant potential for advancement also lies with the discovery and utilization of novel user signals. Indeed, a wide variety of behavioral signals have already been explored to estimate user preferences. Such signals can be explicit in nature, such as user ratings, or implicit, such as time spent viewing specific content. Unfortunately, these data are mere approximations of user interests. Explicit and implicit signals are not always reliable. Users may like or share content they do not otherwise prefer simply because it is outrageous or unusual, and they may spend time attending to particular content for a variety of reasons unrelated to preference. We will demonstrate a novel alternative to estimating user preferences: direct measurement of the human brain. Such an approach does not depend on potentially unreliable explicit or implicit behavioral signals. Instead, it only requires the user to perceive content while their brain signals are recorded. Using electroencephalography, also known as EEG, we reveal neurophysiological markers of graded preference from a realistic preference experiment and show that preferences inferred from EEG recordings can be used successfully in a collaborative filtering setting. Brain-computer interfacing is a paradigm in which the brain activity of an individual is used to control or otherwise influence a digital or mechanical process. There are a variety of brain imaging techniques used in brain-computer interfacing, and EEG is one of the most popular. EEG recordings consist of changes in electrical voltage as measured at the surface of the scalp. These changes in voltage are produced by the synchronized activity of many neurons and thus reflect underlying processes occurring within the brain. EEG recordings have high temporal resolution and low spatial resolution. Thus, it is easy to detect when something has occurred in the brain, but not necessarily where. EEG is also sensitive to other sources of electrical noise and artifacts, such as electrical equipment and transmission lines, or disturbances produced by blinking or moving the eyes. These limitations aside, EEG has been successfully used as a source of data for brain-computer interfaces. A useful feature of EEG signals is the event-related potential, or ERP, which is a change in electrical voltage in response to a specific event. ERPs are produced by a variety of activities, like viewing a face or planning movement of a muscle. They consist of positive and negative components. The P3, sometimes referred to as the P300, is a positive ERP component that is associated with a variety of cognitive events, including surprise and novelty. In this experiment, we utilize the P3 component to detect level of user preference. We study collaborative filtering in the context of personal attraction. People have a natural personal attractiveness response to facial images, and this can be measured from the brain. We designed an experiment that emulated swipe-based dating applications, except rather than subjects using a phone to explore profiles, They simply observed faces presented to them on a computer screen while their EEG recordings were taken. To ensure subjects did not recognize any of the stimuli, which could introduce confounds into the results, we used artificially generated faces, such as the ones shown here. 31 subjects were instructed to look for faces they found personally attractive. Images were displayed in rapid serial visual presentation trials at a rate of 2 images per second. This is what it looks like in practice. In addition to EEG signals, we also recorded explicit behavioral information. After each block of images, subjects were asked to select the faces they had found personally attractive. This procedure was repeated a total of 3 times, and the number of times a subject selected a particular image was used to assign a rating from 0 to 3, analogous to commonly used star ratings. After all data were collected, they were cleaned for artifacts and noise using simple techniques and filters. Next, individual classifier models for each subject were trained, using the explicit ratings as ground truth labels. These models can then take new EEG data as input and provide a preference estimation as output. To rule out the possibility that inferring preferences from brain signals might rely on a highly specialized architecture, we tested several computational methods for both inferring preferences and performing collaborative filtering. For inferring preferences from brain signals, we used linear discriminant analysis and a multilayer perceptron. The collaborative filtering step was tested with 3 methods: singular value decomposition, k-nearest neighbors, and a neurocollaborative filtering architecture as proposed by Hua et al. In 2017. Random baselines were established for both steps. For inferring preferences, we used models trained from random label permutation. For the collaborative filtering step, the random baseline consisted of a rating drawn from a normal distribution, with parameters estimated from the dataset using maximum likelihood estimation. We also compared the brain-based collaborative filtering performance with what could be achieved using existing approaches. To do this, we performed collaborative filtering using the explicit ratings provided by subjects. By averaging the brain responses of all subjects, grouped by explicit rating, we find that level of preference corresponds to an early frontal positivity and a late parietal positivity. The more a subject preferred a face, the larger this positivity. During the preference inference task, both classifiers performed significantly better than the random baseline for an overwhelming majority of subjects. The LDA classifier achieved better performance than the MLP model, which reflects the prevailing understanding that LDA remains a computationally inexpensive approach to achieving state-of-the-art performance with ERP classification. The MLP results could likely be improved by modifying the neural network architecture such that the temporal features present in ERPs are more easily modeled. Nonetheless, both methods produced inferred preferences of a high enough quality where they could be reliably used in collaborative filtering. In the collaborative filtering step, we compared the performance of several different pipelines: LDA plus SVD, LDA plus KNN, and MLP plus NCF. At 10% sparsity, the MLP plus NCF approach achieved the best performance, although at higher levels of sparsity it performed roughly the same as the other methods. All models, across all sparsity levels, produced results that were significantly better than random. Comparing the performance of the brain-based approaches with ones using explicit labels, we find differences that, while statistically significant, are quite small, especially at higher sparsity levels. Comparing changes in per-subject performance between the preference inference and collaborative filtering steps, accuracy significantly improved for the overwhelming majority of subjects. This suggests that meaningful information is being recovered during the collaborative filtering step and that the brain-based model is working as intended. The goal of this research was to answer the following questions. Can brain responses be used to predict user preferences? And can preferences inferred from the brain be used for collaborative filtering? Our results show that it is possible to reliably associate brain responses with self-reported preferences, and that graded preferences can be predicted from brain responses. Our results also show the feasibility of using brain input as an information source for collaborative filtering. All architectures for brain-based collaborative filtering achieved results significantly better than random and with large effect sizes. While the most common ways humans interact with computers involve tactile inputs such as a mouse, keyboard, or touchscreen, as the technology improves, so too does the possibility of brain-computer interfacing becoming a common mode of interaction. This will introduce a variety of exciting possibilities, as well as serious moral and ethical concerns. Careful consideration must be given to how this technology could be misused. Brain imaging techniques are still quite limited in the information they can reliably capture, and currently they are not capable of reading the human mind. However, it is not unreasonable to expect that imaging techniques and the data they produce will continue to improve in the coming years. Organizations that have access to large amounts of user data are already building systems that seem to understand users better than the users understand themselves, and there is a growing concern that these systems are not just being used to improve user experience, but to also influence and direct user behavior based on the interests of third parties. Granting such organizations unrestricted access to data collected from the brain would only exacerbate these disparities. Future BCI systems must be designed such that the data collected cannot be used in ways that a user did not knowingly consent to. This will prove a significant challenge. Widespread adoption of a technology often occurs long before its consequences are fully understood.